Hello and welcome into the Biostatistics and Pharmacoeconomics chapter. We are on page 156 of your book. So this chapter is extremely important for your NAPLEX exam. Please expect quite a bit of questions in this area. This is one of the competency statements on the blueprint for the NAPLEX exam. So you want to be best prepared to answer these questions carefully as well as accurately. So to begin, we're going to talk about some of the areas that you really want to focus on first. They're going to be the absolute risk reduction, relative risk reduction, relative risk, number needed to treat. Also recognize how to determine if something is statistically significant. You know, you can use a p-value for that, or you can use a confidence interval to determine statistical significance. Expect to see abstracts on the exam, and you have to be able to interpret them. So the tools are all in the chapter, and we'll get there in a minute. But first, let's describe some of the basic underlying fundamentals of statistics, define some terms together. So this is what we don't want to have happen on the exam, is you feel confused, don't know how to address the question, and you really want to get quick because it's all about speed and accuracy on the test. So we're not going to have any of this for your exam. So the chapter starts with descriptive statistics. So descriptive statistics, so this is describing the data. And the first three terms that we have are all focused on describing the center of data. So they're called measures of central tendency, or where the center of the data lie. So three different ways to do that. We have the mean. Everybody knows what the mean is. It's an average. We use this in everyday life. It's appropriate for just continuous data that is not skewed. So non-skewed data would be data that follows a bell-shaped curve or a Gaussian curve, and we'll get to that terminology here in a minute. So this is the average. So if you have an example like the one given in your book, you have a series of numbers. Here you have 10 numbers. Obviously, to do the mean, you would just add up all those numbers, get the total of 75, then you would divide by the number of numbers you have, or the number of data points you have, and that is 10. So 75 divided by 10 is 7.5. So that's the mean. Another measure of central tendency is the median. The median is defined as the middle point in a ranked list. It's also known as the 50th percentile. So it's in the middle of a ranked list. Please remember, you have to rank the list first, whether you go from highest to lowest or lowest to highest, but it must be a ranked list. So the median is the measure of central tendency we want to use when we have skewed data, data that does not follow a normal distribution. So this is appropriate for skewed data. So that's very important to know for the exam in case you get an abstract and they tell you that the data is skewed, and they give you mean data and median data. You would want to use the median data to determine the middle point, or the measure of central tendency. So using the same example or the same data set as above, we ranked it. Okay, so we go from lowest to highest, ranking the middle, or ranking the numbers, and then you want to pick the middle number. Now, of course, we have a series of 10 numbers, or an even number, so there is no true middle. So you'd have to take the middle two values that you have, add them up, divide by 2. And so 7 plus 8 we know is 15. Divide by 2, we get 7.5. So one thing I want to stop here and address is maybe they don't tell you on the exam your data is skewed or not. Maybe they just present to you median data and mean data. Well, you can tell your data is not skewed if the median and the mean are similar, or almost, in this case, exact. So if they're very close to each other, you know that your data is not skewed. Okay, the mode. We don't use this too commonly in biomedical statistics. So here, this is the most frequent occurring number. So in this example, we only have one frequent occurring number, and that's 8. You can have multiple modes. You can have no mode as well. So that's not a term we use a lot in analyzing data. Next, we have the range. The range is simply subtracting the highest number in the data set from the lowest number in the data set. So that's the difference between the highest and the lowest value. So here's our highest value, 15. Our lowest value, 1. So 15 minus 1. Our range is 14. That's not a commonly used term in biomedical literature statistics, but you should know what it means. Okay, moving on to normal distribution. So this is a graphic of normal distribution. So the data is normally distributed, and you see we usually call this a bell-shaped curve. So normally distributed data, the middle, this middle line right here, represents your mean, and it's also equal to or very close to your median, because we just said that from the previous discussion that your mean and your median, when they're similar or equal to each other, you know you have non-skewed data. So it's symmetric, no skew. Another way they can describe this type of data on the exam would be that it's a mirror image when plotted of each other. So when you have normally distributed data, bell-shaped curve, and you are able to look at the mean, most of us like to work with the mean because it's a more familiar term to most of us than the median. So we can use the mean. Another parameter that you have now that you have normally distributed data and a mean is a standard deviation. So a standard deviation is the variance from the mean. So how far away are we from the mean? So the variance from the mean. So we usually describe things in 1 standard deviation away and 2 standard deviations away. When you have normally distributed data, that's when you can do standard deviation. When you have standard deviation plus minus 1 away from the mean, as you could see by adding up these numbers here, this accounts for 68% of the patients in that trial. So by having the standard deviation, it's only telling you a little bit more than just the center. That's what the mean tells us. When you have a standard deviation, now you're seeing, okay, what happened to most people in the trial? Roughly 2/3 of the patients in the trial had this result. So that's 68%. If you go out 2 standard deviations from the mean, now you're adding in these values, the 13.6 on each side. And this represents 95% of the patient population. So it's really important when you have normally distributed data to understand the standard deviation, because you would see what most people are experiencing in that trial. So the smaller the standard deviation, so a lower number, the smaller that number, a similar effect is had on most patients. So if you were to draw another graph, this would be a very small standard deviation. It's very tight. Most people in the trial experienced the same quantity or same magnitude of effect. When you have a larger standard deviation, you would expect the bell-shaped curve to be more flattened out. And so by drawing a curve like this compared to a curve like this you obviously know has a higher standard deviation. So 68% of the patients, maybe some really didn't experience a whole great magnitude of effect, where some people really had a significant magnitude of effect from this drug. So the standard deviation tells us what to expect in most patients in that trial. Again, just describing the data. So these are called descriptive statistics. So that was normally distributed data, data that's not skewed. Now let's look at data that is skewed, and this graphic is in your book. So when you have data that's skewed, so of course we're looking at graphic A and graphic C, because graphic B has no skew. This is normally distributed, and we just described how the center represents your mean, median, also your mode, but we talked how that's not commonly used in biomedical literature. When you have skewed data, let's look at figure A first. Your middle of that hump is always the mode. Always the mode. You'll find that too when the data is skewed in the other direction. That middle is always the mode. Next to that, you're going to have the median. The median, as you recall, represents the 50th percentile. So that will always reflect true middle. Always, because that's its definition, 50th percentile. So here on graphic C, same thing, the middle. So 50% of the numbers or data points will be above that line, 50% of the data points will be below that line. So that's the true middle, and that's why when we have skewed data, we use the median to define our middle. And then our mean. You'll see the mean is always near the tail part. The mean is going to be skewed because the data is skewed. There's some outliers out here that's skewing the mean this direction. Okay, in figure C, again, the mean is near the tail because there's some outlier data points out here that's skewing the mean towards that part of the tail. So that's important to know because as you see, this mean is skewed to the left. So this is when data is skewed to the left, we say it's negatively skewed. So it's skewed to the left. Picture C, it's skewed to the right. Because the data out here, these outliers are pulling the mean away from the median. So it's skewing it to the right, and data that's skewed to the right is said to be positively skewed. Okay, so the big overlying principle for this slide is when you have skewed data, make sure you're using the median. So next we have very important concepts. Please make sure you're going to pay attention because this is the meat of the matter when interpreting clinical trials. So we're going to talk about the null hypothesis, the alternative, and the p-value. Then we'll also then discuss the confidence interval. So the null hypothesis, null meaning nothing, nada, no, zip, zilch. So no relationship, no difference, no relationship between the two groups that are being studied. So if we have drug A and drug B in the trial, and if we want to imagine drug B is our placebo, we would still call that an arm of the trial. There would be no difference between the two groups. So when you set up a clinical trial, the null hypothesis is always saying there's no difference. That's what null stands for, 0, right? No difference. So how do we know that the drug does work? Well, we look at the statistical significance of the trial. And if it reaches statistical significance, we would say that we would fail to accept the null, because the null says there is no difference when we found a difference based on statistical significance. So fail to be accepted is the same thing as saying reject. So depending on how they term it on the exam, fail to be accepted or fail to accept or reject. Either one means the same thing. Okay, so we're looking at statistical significance to say if we're going to accept or not accept the null. If we don't accept the null, then of course we're accepting the alternative. If we say no to the null, obviously we're saying yes to the alternative hypothesis. The alternative hypothesis of every trial that's designed is always that there is a difference. There is a relationship between the two groups or between the drug and the outcome of the trial. So they are not equal. One is better. The drug does work at reducing heart attacks. The drug does work at reducing cholesterol. So if we envision that one of the arms is placebo, I think it's easier to gain the concept. Okay, so that's the null and the alternative. So very important to know when you accept the null and when you fail to accept the null, and therefore when you move on to the alternative hypothesis. P-value. Okay, let's talk about p-value. P, you know, stands for probability, so it's the probability value that the result observed is due to random occurrence, or as we like to say, obtained by chance. So it wasn't because of the drug, it was just due to chance that we found a difference. So we don't want this to happen, but we always have a p-value of the trial because it's never, trials are never foolproof, right? There's always some degree of error. Okay, so it's the probability the result was obtained by chance. Here's an important concept to know. Before or when the trial is designed and before it's executed, before people are enrolled, there is a significance level that's defined. That's also called an alpha level. So if they tell you the alpha level of a trial is 0.05, that's the same thing as saying that's the significance level of the trial. The p-value is always less than that number. So that's the significance level or the alpha level. As I mentioned, less, if it's set to 0.05, less than that would be our p-value. So maybe on the exam they don't tell you the p-value, but they do tell you the alpha level, or they tell you the significance level. Then you know the p-value is less than that. Important concept, very important concept. Okay, so p-value is all about statistical significance, not clinical significance. There's a little blurb in your book about the difference between statistical and clinical significance. Just because something is statistically significant doesn't mean that, whoa, we're going to go out and everybody's going to be using this drug because it found some potential benefit. So there's a great example in your book that you can read through if you don't know the difference between statistical and clinical significance. Now let's talk about confidence interval. First, let's describe what it is so you have a clear understanding. So our confidence interval is a range of values, as we know, from a sample, okay, so from one trial we're talking, that has a given probability, everything is about probability in statistics, nothing is a guarantee, of containing the true value. What is this true value? Well, I'll show you in a moment. So the true value is also known as, you may hear it described as the point estimate. The true value or the point estimate. So it tells us the given probability, most of the time we use 95% confidence interval. That's usually our confidence coefficient for most clinical trials. That the population's true value is contained within the interval. Let's go down to the description. Okay, so I'm going to use two examples to try to highlight that definition a bit more. So if we look at one trial where it's talking about newborn weight is 7.7 pounds, confidence interval 6.6 to 8.8 pounds of this one hospital. So therefore, if you sample 100 babies, since it's 95%, 95 of the 100 babies would probably weigh between this confidence interval. So what we're saying, this true value or this point estimate, even if it's not 100% accurate, and we don't know if it's 100% accurate, we would have to say probably not it's 100% accurate. We do know, though, we have 95% confidence that that true value or that point estimate is going to be in this range. 95 out of 100 times it will be in that range. That's what the confidence interval is telling us. So that's the descriptive way of talking about that confidence interval. Let me go back up to this bullet point. So if you are 95% confident, then of course the other percentage left, in this case 5%, you are not confident, so you have uncertainty. So you could see that there is a relationship between the p-value and the confidence interval. So there is a relationship between the p-value and the confidence interval. So if your confidence interval is 95%, you know that your p-value is going to be less than 5% or less than 0.05. Okay, so your confidence interval and your p-value will equal 100%. So another example, I took this from the 4S trial that looked at simvastatin many years ago and got it approved for lowering the risk of cardiovascular events. So the relative risk of death in the 4S trial in the simvastatin group was 0.70. Okay, so this is your relative risk, and we're going to talk about this term here soon. So we know 1 minus relative risk is the relative risk reduction. So we know the relative risk reduction then is 30%. That was very significant. And of course, we saw that it met statistical significance. So even if it wasn't 0.7 or 70%, even if that wasn't the quote true value, but that was the value in these 4,000 some patients we studied, we are 95% confident that that true value would be in this range. So please understand the meaning and the definition of confidence interval. So that's the descriptive way of using confidence interval. That's what it means. That's how we describe the data. We also use confidence interval in an inferential way, a way to compare groups and determine significance, statistical significance. So an inferential way of using confidence interval is really to determine if something is statistically significant or not. So I'm on the bottom of page 159 using the same terminology and example in your book. So there are 2 rules when you're using confidence interval inferentially. So you have 2 rules. If you're looking at the difference between 2 groups, you're going to subtract one group from the other group. And so the column you have would be the difference between the 2 groups. And you look at that confidence interval. If it does not include 0, then the results are significant. And of course, if we're talking about a 95% confidence interval, they're significant at the 0.05 or 5% level. So when you look at the difference between 2 groups, the number you're looking for in that confidence interval is 0. If it's there, then the results are not significant. If it is not there, then the results are significant. Now, if you're looking at data in terms of odds, risk, or hazard ratio, so we say the ratio, because it doesn't matter if it's a risk ratio, a hazard ratio, or an odds ratio, you're now seeing if that confidence interval includes the number 1, and if it does not include the number 1, again, the results are significant. So get comfortable with this. We'll go through an example, and if you like it said another way, here's a shorter way of saying the same thing, the difference or the ratio. Again, if you're looking at the difference between 2 groups, you're looking for that number 0 in the confidence interval. If it is there, so include 0, not significant statistically. The ratio, whether it's an odds ratio, hazard ratio, or a risk ratio, you're looking for the number 1. If 1 is included in that 95% confidence interval, again, not statistically significant. So let's look at the example in your book. So for this example, I'd like you at home there to cover up this last column, the p-value column. Cover that up. Pretend this is a real live example on the exam. And they're asking you to determine if something is statistically significant or not, and you're not given that last column, the p-value. So they just give you these 3 columns, and they tell you, okay, is the change in pre-bronchodilator FEV1, is it statistically significant? Well, we're not going to look at the p-value column. We're going to look here at the difference. Remember, if we're looking at the difference between 2 groups, the number we're looking for in the confidence interval is 0. 18 to 58, does that include the number 0? No, it does not. There is no 0 in this confidence interval. Therefore, the results are significant. Next example, change in pre-bronchodilator FEV1 over FVC in terms of percentage. Again, we're going to look at the difference. So 0.314 minus 0.001 gives us 0.313. But we're looking at the confidence interval here to determine if it's statistically significant. We have difference data, so we're looking for 0. Is 0 in this interval? We go from negative to positive. So yes, 0 is in that interval. So therefore, we are not significant. And we have a p-value there that'll tell you that. So just make sure on the exam you know to determine statistical significance based off of the confidence interval. Okay, example 2, looking at exacerbations. So severe exacerbations, and what's our data set now? Looking at relative risk or risk ratio. So now we have ratio data. So when we have ratio as our endpoint or as our data, we're looking for that number 1, not 0. If 1 is included, which it is here, then we know it's not significant statistically. So, and we see that again by the p-value, but in case that p-value wasn't there on the exam. And here, do we have 1? Nope, almost, but we do not. So of course, if it does not contain 1, it is statistically significant. It's as easy as that. So that was looking at a clinical trial, determining the null hypothesis, the alternative hypothesis, and how to determine if you're going to accept or fail to accept the null hypothesis depending on statistical significance, which can be defined either by the p-value or found by the confidence interval. Now let's move on to correlation. So correlation is not saying cause and effect. We're just saying our two variables or more than two variables, what is their relationship? Do they affect each other? So relationship between two or more variables is its definition. It's frequently described by the Pearson correlation coefficient, which is a little r, and ranges from -1 to 1. A positive correlation, if two variables move in the same direction, we say they are positively correlated. So some examples. So the longer time you spend running, generally the more calories you burn. So the longer the time running, the more calories that are burned, positively correlated. They move in the same direction. Another example, the more fast food one eats per week, generally, unless they have a great metabolism and working out all the time, generally the more weight gain. So those two are positively correlated. Usually it's just determining a relationship, not cause and effect. Negative correlation means that they move in opposite directions. So the examples we have here to show that are example of the first one here, the older the age or as age increases, the agility level of someone generally decreases. Another example, the more self-monitoring of blood sugar in patients with diabetes, the more times they're checking their blood sugar, then they get the data back to say if they're too high or too low. Generally, it's usually is more too high. We would expect less hyperglycemia because they're on top of it. They're getting numbers and they're then taking more insulin if needed. So we would say that those are negatively correlated. The more times you test, more likely the better your blood sugar will be controlled. The more one exercises had been correlated to causing less depression, or not causing, but associated with less depression. So again, negatively correlated. We also call this an inverse relationship. So in terms of looking at the Pearson correlation coefficient, we have some examples here. So this is a strongly positive correlation. So when we are positively correlated, remember our relationship between two values are moving in the same direction. We usually say up, sometimes they both move down. Okay, so that's a strong relationship when your line of best fit through all the data points is measured and drawn of that nature. This is a strong negative correlation, so that's when things are inversely related or the relationship is moving in opposite directions. This is weakly positive because our line of best fit doesn't touch all those variables or touch all those data sets, so we would say that would be more weakly positive, and this would be more weakly negative. Okay, and then here's an example of no relationship. We can't really draw a line of best fit which will touch most of those data points. So if something is not correlated, at all, there's no effect on one variable on another, then we say they are not correlated. And so if you have something that's strongly positively correlated, we call that a +1. Strongly negatively correlated, we call that a -1. No correlation is a 0. So that goes back up to the initial definition when we were talking about the Pearson correlation coefficient. Okay, moving into the types of error you can find in clinical trials. So type 1 error also is defined as the alpha or the alpha error. So denoted by alpha, as you see here, a type 1 error is committed when the null hypothesis is true, but it's rejected in error. Okay, obviously in error because we're talking about type 1 error. So as we said, drug A equals drug B in our example previously, talking about the null hypothesis. Remember, no relationship, so roughly the two arms of the trial are equal. So this is a true statement, but we rejected it in error. Reject in error. So why or when is the only time you reject the null hypothesis? You reject the null hypothesis when you found something to be statistically significant. So if you found this to be statistically significant when in all reality there is no benefit to that drug over placebo, it's like placebo, you're saying there is a benefit when it really isn't. So therefore you're committing a type 1 error and you're saying the drug works when it really doesn't. So why would you have statistical significance? Because you have a type 1 error, and again, due to chance. So the trial met statistical significance due to chance. Okay, so a difference was found when one does not really exist. We talked about the alpha level already, and the p-value is always less than that alpha level. And the p-value is a representation of the magnitude of effect being due to chance, which we saw in this example. You could also call type 1 error false positives. And an example in clinical practice of a type 1 errors, this was maybe before the time of many of you watching these videos, but Xigris was approved back in the late 90s, I want to say, or early 2000. This drug, that's the brand name, the generic name was drogecogen alpha, and it was approved for severe sepsis patients. It had one trial at the time. It was called the Prowess trial. And that trial found a 30% reduction of mortality when you use this drug in patients with severe sepsis, which you know has a very, very high mortality rate. So there was a lot of excitement about the drug. Of course, the drug was very expensively priced, so it was unable to use the drug in healthcare for everybody because it was so expensive. So years have gone by of using this drug, and some people weren't benefiting. The FDA got wind of this. Then the FDA asked the manufacturer to do another trial to determine that it would have the same effect to reduce mortality. And when the Prowess 2 trial was done, there was no difference statistically between drogecogen alpha and placebo. So therefore, after this and a few other things that have gone on at the FDA, usually to get your drug approved nowadays, you need 2 clinical trials because the FDA wants to make sure that the results are seen in both trials. So one of the trials, it didn't have a type 2 error or a type 1 error. So confidence interval is equal to 1 minus alpha. As I mentioned before, the relationship between the p-value or the alpha value and the confidence interval, these two always equal 100% or 1. So type 1 error, it's important to know exactly what a type 1 error is, and also a good way to try to minimize type 1 error, and that would be to do subsequent trials of similar patients and similar endpoints. Type 2 error is also known as beta. And this happens Type 2 error occurs when the null hypothesis is false, but yet it's accepted in error. So that null hypothesis we were talking about before is always set to equal each other, right? Both arms of the trial are equal. One drug is not better than the other, or not better than placebo. So this is actually false. One drug is better, but it's accepted in error. Accepted in error. So why do you, or when do you accept the null hypothesis? You accept the null hypothesis only when you don't have statistically significant results. So you would accept the null hypothesis because you did not reach statistical significance in that trial. Okay, and oftentimes we may not reach statistical significance in a trial because of what? Power, statistical power. The study that was done was underpowered. It didn't have enough patients. It didn't have enough events. So therefore, it wasn't properly done with enough events or enough patients to have the power to show statistical significance. So type 2 error goes hand in hand with statistical power. Okay. Beta or type 2 error is also called a measure of sensitivity, and we're going to get to sensitivity and specificity in a moment. So an example, if we did this trial, not that it's been done, but an example is Lipitor was found to be no different than placebo in reducing cardiovascular events. And we know that that is not true. We know Lipitor does have multiple studies showing that it reduces cardiovascular events. So if we accepted this, it would be accepted in error, and maybe we would accept it because obviously it didn't reach statistical significance. So that's where statistical power comes in, because you have to have enough power of your trial to show a difference between two groups. So defined, it's the probability that the test will reject the null when it is false. So therefore not making a type 2 error. So we need enough statistical power. Power is equal to 1 minus beta, so 1 minus the chance of making a type 2 error. In clinical practice, we generally say our beta is equal to 20% or 0.2. And so if beta is typically 0.2, what's our power? If power is 1 minus beta, 1 minus 0.2, our power is 0.8 or 80%. That's the standard power most trials have. You can go higher, obviously, but generally never accepted to go lower or less power. So statistical power is all about, of course, a few factors that affect it, but the two you really want to know for the exam are going to be to increase your sample size will increase your power, also to increase the event rate. So not only just increasing more patients, but also going after the patients that are going to have the event that we're questioning or looking to reduce. So those are your types of error. Next in the chapter, we have a discussion of our variables, dependent and independent variables. Just as the name suggests, dependent variable depends or changes in response to the intervention, and the intervention is the independent variable. So the intervention of trials usually is a drug, sometimes a device, but generally a drug. So whatever our endpoint, our primary endpoint is that we're looking at is our dependent variable. The drug is the independent variable. So just a simple example of aspirin versus placebo and reducing coronary events. What would be your dependent variable? This would be expected to change in response to the independent variable. So the independent variable is aspirin, and the dependent variable, or the expected change, is the primary outcome, generally, coronary events. There's a description of the types of data that we have used in trials, and this is important to identify the type of data we have in a clinical trial, because that will then reflect on what type of statistical test we want to run for the type of data we have. So just briefly going through this, we have two different types or categories, discrete and continuous. So discrete is made up of nominal data and ordinal data. So discrete nominal is where you have categories and numbers, but they're arbitrary. So here in this example, the first one, male is equal to 0, female equal to 1. You can also switch those, right? You can make the female equal to 0, male equal to 1. It's arbitrary. So that's nominal data, right? So it's just describing the types of data. Oftentimes we look at this as analyzing the type of trial and who did they study and what type of ethnicity, what type of gender, did that affect the outcome at all? So that would be considered the nominal data. It's usually the demographics. Ordinal data is ranked categories, but here the order is important. The order tells us something. It's a measure of severity, a measure of something that correlates with that number. So some examples are the Likert scale. Usually on Likert scales they go from 1 to 5, 1 being you strongly disagree, 2 disagree, 3 neutral. So a lot of times you'll get this when you shop a lot at stores. Likert scales, are you likely to come back? Are you likely to use this airline? So the number does correlate with something. New York Heart Association functional class. If you had heart failure, you'd rather be a class 1 because you're less severe in disease than a class 4 patient. APGAR score is used in our pediatrics when they're born, in our children. Apache score is a measure of how critically ill somebody is after a traumatic event or in an ICU. So those are just some examples of scaled severity scores that we use that would be considered ordinal data. Continuous data, we know it's continuous. It goes on and on and on, so we say it's infinite, and it could be fractional. It doesn't have to be just whole numbers. And two types of continuous data are interval and ratio. So the difference between the two, interval, the 0 point is arbitrary, such as in a temperature scale, whereas most of the time we have ratio data where there isn't an arbitrary 0. The 0 is actually meaningful. It's meaningful not to have any weight. You know, 0 weight obviously means you're not part of this planet, no time, okay? So that is a measurement and it's meaningful. So a lot of times we have ratio data as part of our type of continuous. So depending on the type of data, then you get to say what statistical tests should I run based on the data I'm analyzing. So as I mentioned, we do a lot of trials with continuous data, looking at lowering of LDL, lowering of blood pressure, millimeters of mercury. We're looking at 2 groups, and they're independent samples. A lot of times, we're very familiar with the student t-test. So the type of data, and if you have paired or independent samples, will tell you the type of statistical test that should be run on that data. Now comes to some more meat in this chapter. So this is extremely important. So please make sure that you're going to get these future concepts. We're going to talk about relative risk, also known as risk reduction, or risk ratio, excuse me. Then we're going to talk about relative risk reduction next, number needed to treat, and absolute risk reduction. Those 4 principles are critical, not only in terms of knowing the calculations and being able to calculate them, but also what they mean and when is it appropriate to use RR, RRR, ARR, number needed to treat, in terms of making formulary decisions at hospitals and healthcare plans. So let's dive in. I think the description of relative risk or risk ratio is the most difficult of the 4 we're going to talk about. So let's go through it. We'll go through this one a little bit more slowly and speed it up for the easier concepts to come. So relative risk or risk ratio, whatever you see on the exam, just know that they mean the same thing. They're interchangeable. It's the probability of having an unfavorable event, or you could say a bad outcome, in a treatment group versus comparing it to the control group. So we're looking at the bad outcomes happening in the treatment group versus the bad outcomes happening in the control group. So that's the risk ratio. So we're just putting the treatment group up top, the control group below, and it's giving us, this is going to be our ratio. However, we oftentimes get raw data given to us and not actually the risk ratio calculated for us, or the relative risk calculated for us. So sometimes we have to find and calculate the risk in each group. So the risk in each group, of course, risk is defined as the number of subjects with the unfavorable event in that arm of the study. And it's expressed as a fraction or a percentage. And we're going to go through a few examples. Once you have the risk, then you can move on to the relative risk. So let's go through a really simple example I put over here on the side. We have 10 patients in this trial. And we randomized 4 to drug X and 6 to placebo. So that's our raw data. We don't have the risk yet. Further, it's defined that we're looking at this drug to reduce pain. And of those 4 patients that got drug X, 1 patient is still in pain. You would say that the bad outcome is to be pain-free or with pain. Obviously with pain. So this is a measure of the unfavorable or bad outcome. Of the 6 patients randomized to placebo, 5 of them are still in pain. Okay, so this is just the raw data. Now we have to calculate the risk of pain in each of the arms. So the bad thing happening is pain. So we have 1 out of 4 randomized to this arm of the trial. Remember, risk is per arm of the study. So 1 divided by 4, our risk is 0.25 or 25% risk of having pain. 6 patients in the total arm of this study, 5 in pain. So our treatment group goes up top, or the unfavorable event up top. The total number of patients in that arm is 6. Divide that out, we get 0.83, or 83% of patients still having pain. And then our risk ratio, now that we have our risk measured for us, now we could do the ratio. And so to do the ratio, you'd put the treatment group up top, the control group down bottom. So 0.25 divided by 0.83 gives us a risk ratio of 0.3, or 30%. Okay, so this is an important formula to know. Risk of the treatment group is always in the numerator, control group always in the denominator. So risk has to be given to you. If it's not, then you have to calculate it using this formula here. Okay, so 2 formulas there. We're going to do another example that is coming up in your book here soon. So what does that mean when you get this number back? Well, here are the rules. Please know these rules. If you have a risk ratio of 1, obviously you would have the same number over the same number, and that's how you get 1. There is no difference in risk. So if this was 0.25 and this was 0.25, when you did 0.25 over 0.25, obviously the risk is 1. There's no difference if you use drug X or placebo. So it's saying there's no difference between 2 groups, so you're basically saying the drug you're looking at works just like placebo. No difference. So no difference in risk. Relative risk less than 1. So as in this case, 0.3 is less than 1, so you have to use the fraction part. If it's less than 1, now you're saying there's fewer events in those taking the treatment. And we did see that in this trial. Fewer events, 1 patient versus 5. Fewer events, 25% versus 83% having the bad outcome. So there are fewer events. If you have greater than 1, that means your numerator is going to be larger than your denominator. So obviously, there's going to be more events if this number up top in the numerator is higher. So more events in the treatment group, so that's usually not a good thing. We usually want drugs to help our patients, not hurt our patients. So relative risk greater than 1 would mean there'd be more events in the treatment group. Relative risk is not telling us statistical significance or not. Relative risk, remember the definition, we're only comparing the probability of the unfavorable event in both groups. We're not saying if it's statistically significant or not. Okay, so I put these rules here again, for you to refer to. Let's go over example 1 in your book. So you have heart failure patients. Here are the results that you get in from that trial. Lots of patients in the metoprolol group versus the placebo group. And they give you the incidence of heart failure progression in terms of percentage. And on the next line, we have the death rate, 1.9% versus 3.3% in the placebo group. So it asks for us to calculate the relative risk of the incidence of heart failure progression or disease progression. So therefore, we know we're looking at this row only. And we already have the risk calculated for us. So we don't have to do that first step in calculating the risk. It's already calculated for us. So now we just have to do our ratio. We put of course, the treatment group, 16% in the numerator. The denominator is our control group, 16 divided by 28.57. So if you keep it as a percentage, when you calculate it out, the percentage disappears. If you keep it as a decimal, it's both the same answer. So I don't want you to get that confused on the exam. Some people think if I divide a percentage by a percentage, my answer should be a percentage. That's not true. The percentage sign goes away. So whether you use the whole number or the fractional number, you still get the same number of 0.57. Okay, so what does this 0.57 or 57% mean? This is the hard part. Subjects treated with metoprolol, so you're always looking at the group that receives the active drug or the drug in question, were only 57%, and we use the term as likely because we're comparing two groups. We're not saying if they're less likely or more likely. We're just comparing them side by side. So we always use as likely as placebo-treated patients. So we're talking about the active drug that we're comparing to the control arm. And we're saying, okay, how do they compare against each other in terms of the endpoint? So putting this into words could be a little tricky for some. So a couple of rules. We're always talking about what we put in our numerator, which is our drug group, so metoprolol, and they were only 57%, so we're using our calculated number. As likely, we're not saying more likely, we're not saying less likely. This is actually looks like less likely because 57% is less than 100%, right? Because less than 1, we were saying that the treatment group had less events or fewer events, but we're not able to say it because if we say less likely, we're interpreting that when we hear that to mean it's statistically significant. And we didn't do any statistics on this yet. Maybe this isn't statistically significant. Maybe it is. So we have to use the term as likely when we're using risk ratio. As the placebo-treated patients or your denominator goes next, and then at the end of the sentence should be the endpoint that's in question. So that concludes Biostatistics Part 1.